welcome to module 2, lecture 2, and we shall be continuing with aggregates. If you recall, last time we talked about shape and sizes of aggregate, and now in this one we shall be looking into how these sizes affect the packing characteristics of aggregates. So, continuing from the same place where we did last class, we looked into packing characteristics due to shape, how shape improves the packing, and this time we will look into packing and grading, fineness modulus, and we shall also define a term called surface modulus. Now, recall that aggregates are inert material. Aggregates are inert material. They are inert material supposed to form the skeleton of concrete, and for economy in normal concrete one would like to minimize the volume of paste, in other words maximize aggregate volume fraction. So, paste contains cement and that is the costliest material in the concrete. Therefore, one would like to minimize the use of paste from that point of view, from the cost point of view. Of course, there are other issues related to shrinkage etc., but from sheer cost point of view one would like to minimize the use of paste. So, maximize the amount of aggregate in the system. Now, where does paste go? Paste actually goes into the interstitial void space of aggregate. Interstitial void space in the dry aggregate system contains paste, and when one puts this paste inside or mixes them together, there is an alteration of the space. This void space in the aggregate is altered, right. Void space in aggregate is altered when paste is introduced. So, paste required to ensure dispersion of aggregates is higher than the interstitial porosity of the aggregate, and it is desirable to minimize the aggregate porosity or void content. So, when you add paste into the aggregate system, in fact, paste goes into the interstices of the aggregate. Now, if you pack the aggregates alone, you get a void content or void space, which you can define in terms of porosity. When you actually introduce paste and mix them together, the interstitial space within the aggregate actually is changed because of the presence of paste. It is not same as the original porosity without the paste, right, and this paste causes dispersion of the aggregates. They separate the aggregate, fill in the space and separate the aggregate, right. Now, packing density we define as the volume of solids in unit bulk volume. So, if I have total volume V and volume of solids, let us say, is V s, this is volume of pores, then packing density will be V s divided by V, this is total is V, which is equals to V s plus V p. So, you can see that P, if P is the porosity, then V p over V is P. So, V s by V is equals to 1 plus V p by V. So, therefore, V s by V, V s by V plus V p by V is equals to 1, and that is actually volume of pores. So, 1 minus P, P is the porosity. So, packing density is the volume of solid volume of solid in the whole system, and it is given by 1 minus p. It is given by 1 minus p. Packing density of single sized particle is relatively low and depends on packing arrangement. Packing density of single sized particles is relatively low, right, and you can see that, we can understand that very simply. This will be, because supposing I have got all single sized particle and they are packed like this. So, this is called simple cubic packing, and you can consider in the other direction also, other direction the same packing, other direction, 3 dimensional same sort of packing, right, just one below the other. This is called simple cubic packing. Then the void content I can find out. I can find out the void content or porosity, because two particles, all particles are touching each other. So, therefore, if I find out this volume, so volume of solid will be this and total volume will be. So, if the diameter of the particle is d, d cube will be my total V, and Vs will be equals to pi d cube by 6. So, porosity would be so porosity will be, if d cube, so porosity will be given by 1 minus Vs by V, that is equals to P, and this will be given as 1 minus pi d cube by 6 by d cube. So, which will be simply 1 minus pi by 6, and this will be somewhere close to 0.48. So, for simple cubic packing, the porosity is simply 48%. So, for a single sized particle, porosity is fixed and depends upon type of packing, right. Packing density of simple cubic, body centered cubic and face centered cubic arrangements are 0.52, 0.68 and 0.74. So, simple cubic packings were like this, each particle is just by the side of it, and we have seen the P is equals to 0.48, hence packing density is 0.52. Now, consider this kind of arrangement, let us say another arrangement where these particles are sitting inside. Okay, let me erase the previous one out. Let me erase the previous one out and just see. Supposing that my packing is now like this, and the next layer it is coming in between. So, actually packing density would change now. The void should be relatively less, and you can show that for this arrangement packing density will be higher than 0.52. So, depending upon type of packing, for example, for face centered cubic arrangement and body centered cubic arrangement, body centered cubic arrangement it is like this, face centered cubic arrangement it is 0.74. So, it depends upon the kept packing and independent of the size, because if you recall, the size d cube got cancelled, therefore, it is independent of the size and depends upon the packing characteristics. Well, actual packing density of single side sphere will lie somewhere in between, I mean it will lie between these two. You can have best packing or the worst packing, random packing can have something anywhere in between. That is why if you recall, we define we defined something like for rounded aggregate, the packing density was defined as 0.67 when we tried to in relation to when we are talking of shape. So, to define shape we used angularity, the some angularity index we used, where we used the packing density as 0.67. However, multi-side size mixtures have higher packing density. Thus, to have higher packing density, aggregates of different sizes are used. How is it? Let us first look at it simply. Supposing this is my particles and they are packed, let us say again simple cubic packing. Now, let me put another aggregate. Let me put another aggregate finer in between. In that case, packing density of the aggregate will be reduced. In that case, packing density of the aggregate will be reduced. And let me then put still another aggregate somewhere there, still finer, I can put still finer one, right, still finer one I can put in, very fine, I can put in still finer one somewhere there, somewhere there. So, you can see if I use more than one size, multi-size mixtures have higher packing density. Now, the solids are more, the voids have become less. Thus, to have higher packing density, aggregate of different sizes are used. So, you do not use single sized aggregate essentially because single sized aggregate will always pack to a low packing density or high porosity. When you use more than one size, packing density is improved and thereby void space or porosity is reduced. Hence, your paste content will be less. Not only that, proportions of different size fractions shall be appropriate for maximization of packing density. So, size ratio, and one thing is size ratio. Size ratio is size ratio, this is an important issue, and proportions are important issue. Size ratio means maximum size, let us say is 75, minimum size let us say is 75 micron, then next size let us say is x. So, one size is x, next size is y, ratio of this y by x, this is size ratio. And we said that this quotient generally we use as 2. So, this size ratio is important, it is 2 is good enough, but if it is 1 let us say, then it is with the same size. So, it is not going to have any effect. So, size ratio has some effect, 2 is good enough, and that is why you use the quotient, size quotient to define the sizes as 2. Recall that we are talking about the square sieve size, and the ratio of sizes we actually size quotient to use as 2, we use 2. So, size ratio is important, proportion is also important, it is very important to have the proportions. So proportions would make it the maximization of the packing density is possible depending upon the proportions of each size fraction, Now, this can be explained very easily considering a binary mixture. Let us see how packing density increases with addition of another size material. We can understand this much easily. Obviously, degree of improvement depends upon size ratio I have already mentioned, and let us look into how does it improve. Packing of binary system is very easy to understand. Let us say I have two aggregates A and B, right. Let us say B is a coarse size, A is finer, and we are assuming spherical for simplicity. We are considering each factor independently. First we looked into shape and we said that rounded shape packs better. The void ratio increases with going from rounded to angular shape. So, therefore, spherical one packs better, and we are just now considering the effect of different sizes and their proportions on the packing density. So, we are considering spherical particle again, not changing the shape. So, it will be something like this. Supposing you have got all fine materials, this is let us say is A and this is B. So, if you add small amount of B to A, if you add small amount of B to A, right, this is A and this is B, total volume will increase. Total volume will increase by this quantity. Total volume will increase. I have just put them inside and I can find out how the void ratio would change. What is void ratio? Volume of voids divided by volume of solid, or volume of pores divided by volume of solid. So, we define void ratio as volume of pores divided by volume of solid, and which is V minus V is the total volume. So, V minus divided by Vs. So, V by Vs. So, we can write void ratio as V divided by volume of solid minus 1, right. So, this is what we can write for void ratio, and let us see how it would change. Now, void ratio of A alone will be volume of overall volume. It it's let us say A fills the total volume alone divided by volume of solids of A minus 1, because we have defined the void ratio earlier by this equation. Void ratio we have defined by this equation V by Vs minus 1. This is the total volume, the volume of solid minus 1. So, that is the void ratio. So, void ratio of A alone, void ratio of A alone will be V divided by VSA, that is the solid volume in total V minus 1, right. So, VA, VS A are overall volume and solid volume of A in the system. Void ratio of B is V divided by VSB, VSB minus 1. That means, if I fill in the whole system with B alone, then the volume of solid that would occupy is given by this. Now, just look at, so this was the thing, just consider a small amount of B is added to fine A. This is my A and I have just added small amount of B. Packing of fines remaining undisturbed. Total volume is sum of bulk volume of A and solid volume of B. Supposing I just add, this is just added this, right. So, total volume will I just added this. Let us say even if I mix it properly, we are assuming that this volume packing of this one will not be disturbed largely. Packing of fines remaining undisturbed, I just add from top. Total volume of sum of bulk volume of A and solid volume of B. So, total volume will be this bulk volume of A plus solid volume of B, and solid volume is the sum of solid volume of A plus solid volume of B, sum of solid volume of A plus solid volume of B. So, total volume is the sum of bulk volume of A plus the solid volume of B, and volume of solid is the solid volume of A plus solid volume of B. So, using this, if I use this algebra to find out the void ratio, volume fraction of B in total solid of course will be BB divided by VA plus BB, right. Let me define this as a variable x. So, if x is the variable, BB by VA plus BB. So, that x is the volume fraction of B in total solid. VA, BB are solid volume of A and B, as we have understood. Then Ex, that is the void, as a function of this can be written as V plus BB. Now, what is this V plus BB? V was the original volume. So, this is V, this volume is V plus the BB, that is the volume of total volume, increase in total volume. So, this is a new total volume, because we said volume of total volume will be the increase in to volume of A, volume of bulk volume of A plus the solid volume of B. So, this is the total volume, this total volume, and this is a solid volume, because volume of solid of A plus volume of. So, if I add a small quantity of coarse aggregate, quartz size fraction aggregate to bulk finer sized aggregate, then what it will do? It will increase the bulk volume by the amount that I have added, the solid volume that I have added. For example, VB is the solid volume of the coarse aggregate B I have added, and V was the total volume, that is volume of solid plus volume of pores of A. So, if I add this, it will just increase the total volume without increasing the pores, let us say without disturbing the porosity of the fine aggregate. In that case, the volume of total volume will be V plus V B and volume of solid will be this. So, my void ratio by definition would be V plus V B, V S A plus V B, because we said in the V volume V S A is the amount of solid minus 1, and I can write it like this V by V S A, right. If I can write it like this, V by 2 component I am separating out, because V can be written as V S A plus V B. So, I can write it out like this, V, multiply both side by this term, V by V S A plus V B can be written as V by V S A multiplied by V S A by V S A plus V B. So, what is this actually? This is the total volume divided by volume of solid, and this is packing density, packing density of the whole thing. So, anyway, I have just separated out so that I can take something common. So, let us see how the algebra works. Let us just see how this algebra works. So, this is what I have done, modified this term, this divided by this term, and the next would be V by V S A, this term remains same, and this I can write as 1 minus V S B, because V S A is equals to 1 minus V S B divided by V S A plus V B, all right. So, 1 minus V S A, so that is what I can write, I can write V 1 minus V S A plus V B, because V S A is nothing but V S A plus V S B is equals to 1, that is what we are assuming total volume, right. V is this volume and total volume is 1. So, volume fraction, this is volume fraction in the final mix is this. So, I am writing it like this, and if I define x, what was the x? X definition of x was V S B divided by V S A total volume V B. So, this was this is the total volume, that is fraction of solid volume of B in the total volume, that is what we defined as x. So, this will be this is actually this is this is x, and this is also x, because by definition and minus 1. So, I can write as V by V S A 1 minus x plus x minus 1, and I can take common 1 minus x, I can take common. So, if I take 1 minus x common, I will get V by V S A minus 1. So, this is by definition E A. So, this is by definition the void ratio of A alone, void ratio of A alone. This is by definition void ratio of A alone. Let me repeat this process. What I have done? I have added some coarse aggregate into the fine system. If I just add a few of them and maybe push it a little bit from the top, little bit small amount, it is unlikely to disturb the packing characteristics of a fine aggregate too much, because fine aggregate quantity is very large. Only a small quantity, 1 or 2 pieces, let us say I have added of the coarse aggregate B. So, it will not disturb the overall packing of the fine aggregate, minimal disturbance. Ideal case, it is actually really, it does not happen that way, but ideal case let us assume. So, in that case total volume will now increase, because I have added some material, and that will heap up or increase the total volume by how much? By the solid volume of the coarse aggregate that I have added. Solid volume will also increase by the same amount. So, I can express the void ratio, that is the original volume plus the volume of the solid, and let us, we are in our algebraic expression we are assuming V as the original volume. So, V plus V B, that is I have added volume of solid I have added, divided by V S A plus V B is the total volume, minus 1 is the porosity by definition. Then I am doing a little bit of algebraic manipulation. small algebraic manipulation. What is that manipulation? V by, I just take this term out and write it in this manner, multiply top and bottom by VSA, and this term I keep it as it is. The volume of the solid VB, V is the, because this is the amount I have added, VB is the amount I have added, solid I have added in the overall system. So, VSB divided by VSA plus BB, because there is no other solid volume. So, BB is nothing but BSB. I have just written it like this. This I could have written BSB as well, or same thing, because BB is same as BSB. So, I have just written it like this. Now, this VSA is 1 minus BSB, because my total volume is 1. Total volume is 1, and B is the original volume. So, this is original volume and total volume is 1. So, I am just writing it separately in this manner, right, because original volume V, and this original volume I am using to define the VS. In the same total volume, original volume V, the EA will be defined as VSA divided by VA. If alone it was packed, VSA divided by V minus 1. So, or if alone it was packed, if it was packed alone, then the volume that it occupied. So, that is how, this is nothing but EA. So, EA into 1 minus x. So, that is how we come across, that is, it will reduce linearly as I increase the volume fraction of B. So, from the previous one, what we have seen is when we add a small volume of coarse fraction, aggregate, coarse aggregate, the void ratio reduces linearly with x, which is nothing but volume of total volume. So, proportion, it reduces with the proportion of solid volume of B. It reduces, because the expression is, if you recall the expression was EA void ratio reduces 1 minus x, and x by definition is VSA divided by VS plus BB. By definition x was something like this. We have defined x as VB divided by VA, or I can say VSB divided by VSA plus VSB. So, that is how I define the volume fraction of coarse solid in the total volume. All right. So, that is what it is. So, we see that it reduces linearly. Now, let us look at from another angle. Consider small amount of fine aggregate A, added to coarse aggregate B, this should be B. Packing of B remaining undisturbed, bulk volume of B is the total volume of for solid, total bulk volume of B is the total volume for solid volumes of A and B. Okay, let us just see, the diagram will make this statement very clear. What we are trying to say is, supposing I have got now all large particle B, and I am trying to adding a small amount of fine particles. So, they will simply go into the interstices of the coarse particle. They will simply go into the interstices, occupy these spaces, simply they will go into this space. This volume is my V, original volume V of the which was packed with coarse particle. So, this packing of this one will not get disturbed, because I have put in a few particles, it is not going to disturb this, no way it is going to disturb. So, it will remain same, right. Packing of B will remain same, packing of B will remain same, A will particle A will all go inside. So, what will happen to the total solid volume? Total volume remains same. So, total volume, bulk volume, total bulk volume will remain same. Previous case bulk volume increased, but here bulk volume will remain same. Bulk volume will remain same. Volume of solid will increase. Volume of solid will be equals to VSB, which was there originally, or VB, whatever you call it, plus volume of solid that you have added right now, these two volumes. So, this solid volume will increase by this quantity that you have added. So, therefore, Ex, that is the porosity or void ratio as a function, V is the bulk volume has remained same. This was the volume of the solid that you have, the original volume of the solid and the volume of aggregate that you have added. Original volume remained same, minus 1, because we remember this was Vs minus 1. So, Vs has just increased by this small amount of A that you have added, minus 1. Again, I do a little bit of algebraic manipulation, and what I do, B can be separated out as V can be separated out as it's, just multiplied by top and bottom by BSB both sides. So, I just multiply by this VSB, no separation here, simply multiply this by, because I want to get x and this is my x, So, I want to get x. So, what I have done, I have just multiplied by this. So, this gives me V by BSB x minus 1, right. So, Ex is equals to V by BSB x minus 1, and then what I do is I just add minus x and plus x. So, I just just to a little bit more algebraic manipulation, this I add minus x, add x, subtract x, and if I do, then this x gets common. So, I will have B by BSB minus 1, because this is what I want to get, which is nothing but the EB, void ratio of B alone. So, I wanted to get void ratio of B alone, and for that I must subtract x out of this. So, x if I take common, I get like this, and this is x minus 1. So, what I get is EB x plus x minus 1, EB x plus x minus 1, or I can write that x into 1 plus EB minus 1, that is the again linearly related to x, as my x increases, as my x increases, x reduces. Here x will be reducing, because x is the proportion of coarse aggregate in the system. So, as my x reduces, we will find that this void ratio, smaller the x, void ratio will reduce. So, if you two things we have observed from our discussion so far, physically you can understand, when you add small amount of fine aggregate into a otherwise packed system of coarse aggregate, the fine aggregate will simply occupy the interstitial space within the coarse aggregate, thereby reduce the void volume. That sort is manifested in the void ratio. It so happens that void ratio reduces linearly. Algebraically you can show that void ratio will reduce linearly. Similarly, when you add in a packed system of fine spherical particle, I will say, or aggregate, some large coarse particle, very small quantity, it will again reduce down the void in the system, because you will add only some solids, total volume will increase, solid volume will also increase, void volume remaining same as the original, that was the void volume in the fines. The void now void void quantity remaining same, that was there in the original fines. So, void ratio or porosity will reduce, because volume of voids in the total volume has reduced. This we can draw in a manner like as a function of x, for example, void ratio, and this is my x actually, the x is increasing along this direction, x is increasing along this direction, because we said B fraction is 1, volume of B, this fraction, and this is 0 here. So, x is 0 here and 1 here. The the proportion, we are saying that x is nothing but volume of coarse aggregate in the total volume. So, here it is 1, that is all coarse aggregate, and here it is all fine aggregate, and in between I will have different values of x. So, E A stands for the void ratio of A alone. So, when I have only A, this is the void ratio of A. When I add B, a little bit of B, void ratio reduces down, and similarly here it is E B initially, and as I add a little bit of A, in other words reduce down the volume of B, the void ratio should reduce in this manner linearly with x. So, this is my x, it reduces as the x reduces from 1 to smaller value, E B reduces. That is what we have seen through those equations. This is what happens if I add a very small quantity, and if the same thing was happening, then ideally I should have a minimum void somewhere there at some proportion, but in reality what happens is actually you get a curve like this. If you calculate out the void ratio, experimentally try to determine them at different proportion of two binary mixtures, two mixtures, only two sizes you have taken, spherical particle, let us say marble balls, playing marbles or small balls you have taken, then you will get this sort of a relationship of void ratio versus volume fraction. This occurs because of our assumption was that the packing characteristics of the fine aggregate will not be disturbed if I add coarse aggregate, no new pores will be created. Similarly, when we added fine aggregate to coarse system, it will simply reduce down the voids going into the interstices of the coarse aggregate, that is what we assume. But in reality what happens is, for a small amount this may remain valid. You can imagine that, for example, if you have a box containing large size spherical balls, you put few more small balls, they will just go trickle down and sit somewhere inside. But when you start putting more and more, a time will come when this particle will push the larger particle away. In other words, it will disturb the packing of the larger particle. Not only that, they themselves, their packing will not be their ideal packing which they were actually having when they were packed alone. For example, fine aggregate, if you pack alone, you get a kind of packing, you get a voids, but if you put the same fine aggregate in a coarse system, interstices of the coarse system, the void content will not be same as that, rather it will increase. So, because of this kind of behavior, that packing get disturbed, what we call particle interference. When you put another particle, it will interfere with the original system, and thus how the curve never remains straight line, rather it goes as a it becomes curvilinear, rather it tends to become curvilinear in this direction, and the void ratio is much higher than what you would have got for an ideal case. But one thing interesting is, by and large at this point you will have minimum, near this point you will have the minimum packing. So, minimum packing will be very close to what you would have found out even in case of ideal case. So, but the important point here is, there is a specific proportion of this volume of proportion of B and A where this will be minimum. That means, it is not independent of the proportion, the minimum, maximum, minimum void content is a function of the proportion of B in A, or otherwise you can say proportion of A in B. Thus, E x can be represented in a two lines intersecting at x star, that is what we just said, we have just shown x star, x star is the intersection point, this is my x star, right, x star, and you can calculate out this x star algebraically, because from this side if I calculate out, from this side if I calculate out, it is given as x star 1 plus E b minus 1, that must be equals to E a 1 minus x star, because x is same for both, and just simply from this you can calculate out, eliminate out, I mean you can get an expression for x star, you bring it this side, and E b, and this side you have got x star E a. So, if you with a negative sign, so if you bring it to the other side, coefficient of x will be 1 plus E a plus E b, and this term is independent of x star. So, it goes to the other side. So, you will have E a plus 1, divided by this. So, x star can be algebraically evaluated as this, and that is the optimal proportion at which void ratio will be minimum. In other words, packing density will be maximum, packing density will be maximum, packing density will be maximum. Actual behavior is represented by the curve due to particle interference. This is represented by curve because of particle interference. But the point I am trying to make, the point that I am trying to make is that proportion is important, size ratio is important, and obviously you should have more than one size. So, you take two sizes, packing density improves, that is void ratio will reduce, but the amount of reduction of the void ratio depends upon the proportion. So, proportion is important, obviously size ratio is also important, and shape we have seen earlier. Now, there are two effects which are recognized. One is called wall effect. For example, if you see this is my coarse aggregate, if you see this is my coarse aggregate, this is the coarse aggregate and this is the fine aggregate. The packing here is unlikely to be very good. You know, it is not packing like bulk packing, because in front of a large surface or large surface, this packing is never good. This we call as wall effect and it is recognized everywhere. So, this dotted line in the boundary where the wall effect actually increases the pores. So, you can see the packing of the fine particle, finer particle, here we have not taken spherical, but we are showing some sort of regular particle. Packing of the fine particle itself getting disturbed because of presence of the coarse aggregate, quartz particle. So, quartz particle causing a disturbance, this is called wall effect, and this particle inside will be pushing the particle out. So, its sphere of this particle is something like that, and if the voids otherwise were smaller, now this particle depending upon its size it will push out. So, this is called loosening effect. So, wall effect and loosening effect, these are the part of the particle interference, and due to this packing density of the both quartz and the finer one gets disturbed. So, loosening effects cause disturbances in the packing characteristics or void content in the quartz particle, while wall effect cause increase and cause an increase in the void content of the fine particle which has gone inside the quartz particle. So, that is these two effect causes the curvilinear behavior. So, you can see that both together is causing, both together is causing wall effect and loosening effect in a large aggregate. This is your aggregate, 2 is the fine aggregate, these are the additional voids which have come in, additional because of additional voids that is coming. So, particle interference is occurring here, etc. If I calculate packing density of the binary mixture, dP, let me call it as packing density, and I have defined it like this, which is 1 minus P, which is 1 minus P, then Ex is V divided by Vs minus 1. So, this is nothing but the 1 by packing density. So, dpx minus 1. In other words, I can write 1 by dpx is equals to 1 plus Ex, right, and this graph will now look like this. If I plot with x, Ex is known to it. So, packing density if I try to plot with x, because Ex is known, if I try to plot it with x, equations where x were available, this is for 1 minus x, Ea into 1 minus x if you recall, and from this side it will be again Ex expressions were available, and this will give me a something like curve, nonlinear curve of this kind, and from this side also again if I plot at same x star, you will have maximum packing density. So, initially packing density increases with addition of second size, but increases less after due to some particle interference, and you can see that something like this will occur following this form of a curve. So, this would have been the ideal case, but real case is something like this because of the particle interference. Ideal case would have been something like this following this equation this side. The real case is somewhat different. Ideal case coming from this side, real case will be something like this. So, packing density is something of this kind. As x increases, there is a peak, the peak of course remains same at x star which we have evaluated. So, idea of this binary mixture is that if you mix two particles, packing density increases, not ideally, but in some manner, right, but it increases and it has got a maximum at some proportion of the quartz fraction in the total, or some proportion of which is same as fine. Now, I can extend this idea of this binary mixtures to ternary, quaternary and so on so forth. So, idea of this can be extended to multinary mixtures as well, to show that packing density improves with each subsequent addition of sizes. So, you add two size, you add the third size with appropriate size ratio, packing density will improve. Add a fourth size and packing density will increase further. Fifth size, packing density will increase further and so on. So, as many sizes you add, packing density increases. Therefore, we do not use single sized particle in concrete aggregate system, we use large number of sizes varying from smallest size of 75 micron, because we can't use silt and clay, they have other problems. We will discuss that sometime later on. So, sand size which are largely inert do not hold on to particles very close to their surface, because surface forces are not so dominant in sand. In silt, somewhat cement particles might get stick to it, etc., etc. There are problems which we shall discuss, but sand is inert, they do not stick to each other, neither do will cause any kind of problem. So, use sand which is 75 micron and above to as many large sizes possible, maximum size possible. The use of maximum size has other effect of course, but positive effect is it will improve the packing density. Other negative effect we will consider later on. So, optimal fraction also we can identify, you can identify also the optimal fraction, and therefore, to ensure dispersion and to take care of particle interference, amount of mortar used in the aggregate system is little more than the voids corresponding to maximum packing density in the coarse aggregate. For normal concrete, practical grading curves are proposed in the code to ensure appropriate range of size fraction in overall aggregate system. So, what we do is the grading system is nothing, it tells us what proportion of what size one should use. With the current concepts of packing density, perhaps one can determine this algebraically, knowing certain properties of the aggregates, but earlier when such concepts of particle packings were not so well developed, people suggested grading, which actually states how much proportion of which particle should be used in your mix. Actually, grading ranges were suggested from experience, so that minimum proportion of a particular size and the maximum proportion of a particular size in a mix have been specified, and these are given in code. Of course, we have taken care of the aspect of particle packing etc., simply from experience or empirical observation. For best result, amount of mortar should be slightly more, because particle interference will be there. Therefore, amount of mortar in the aggregate should be slightly more than the void content in the coarse aggregate, and it should be slightly mortar should be slightly more in the system, and in the mortar sand, if you look at the packing characteristics of the sand, paste should be slightly more than that in the sand itself. Okay, this concept we will still use when we look into fresh concrete. So, lowest size we say is 75 micron, because that is the sand size. Thus, increasing nominal maximum size of aggregate implies increasing number of size by 1. So, if you are using maximum size as 20 mm and now you decide to use 40 mm, it means that you have added one more size, which means my packing density will increase and I can use less paste, right. So, addition of one more size is very important, and therefore, overall voids in the aggregate would thus reduce by increasing MSA. So, this we have understood now, and the paste required will be less. So, increase MSA or maximum size of aggregate, your paste required will be less. The grading requirement in the table is for all aggregates, separate grading required are also given in code. So, you see this is why the code gives you tabular form, suggestion of grading, the grading requirements are suggested, that gives you the range of the sizes that should be present in an overall aggregate system. For fine aggregates, of course, we define grading zones depending upon, of course, in Indian code as well as in BS code, the grading zones are defined. For finest zone is the zone 4 and zone 1 is the coarsest, because fine aggregate themselves quite often they may be natural sand, river sand. So, they have their grading, there are different proportions of sizes, and according to the sizes generally prevails, 4 grading zones have been actually specified or defined, and zone fine is the most fine, zone 1 is the coarsest. Then we define something called fineness modulus. It is another common way of defining size of fine aggregate or even total aggregate. You talk in terms of an average size, we will just look into this. This is typical grading requirements. So, if you have a SIEP's designations are given, if it is a 20 mm aggregate, if it is a 20 mm aggregate MSA 40 mm, then 100% must be passing through this 95 to 100% grading requirement given in code. So, this is the grading requirement given in code, a tabular form. So, it says that if it is a 40 mm MSA, best result you will get when 40 mm 80 mm through 100% should pass through 80 mm, in 40 mm 90 to 100 and 200 100% should 20 mm 100% should pass through it, etc., etc. So, for 40 mm MSA this is the grading requirement, for 20 mm MSA this is the grading requirement. So, such grading requirement in terms of the range of sizes are given in code, and that should be used in order to satisfy the best, to get the best possible packing. These were actually determined empirically. Right, from experience people have actually suggested. But as I said, modern concepts of particle packing are also available. Let us look at typical grading curve. Well, I think I must be having a typical grading curve. Just let me have a look at typical grading curve if I have one. May not have right now. So, we will see it in the next class maybe. We have a typical grading curve. Typical grading curve, it looks something like this, they look something like this. Percentage passing, SIEP size on this side, percentage passing. So, if you have 100% 20 mm 40 mm MSL, let us say 100% passing, something like this, etc., etc. So, these are typical grading curves are plotted like this. I must be having somewhere, I will just come to that sometime later on. Right. So, now what we have discussed so far is we have looked into the effect of sizes, proportions of different sizes, particle packing, etc., etc. We will just look into fineness modulus, one more concept. We will start this and continue with this in the next class together with the surface modulus which I mentioned. So, fineness modulus, you see, if since size varies logarithmically, weighted average can be obtained as pi log d size. I can take average size. So, I take weighted average size. This is the proportion of total aggregate. So, I talk in terms of pi divided by sigma pi log di. This is the weightage function. So, log of diameter. So, this is what one can use, right. So, average if I want to calculate out, I should use here weighted average one could have possibly averaged it in form of a geometric mean. In fact, that is what we are trying to do. So, a weighted average or geometric mean you can look into, and that is what we are trying to do. And instead, so average, we get the average SIB number. So, this fineness modulus concept I will define, I will explain in the next class, because this would take a little bit of time. And we define fineness modulus as the weighted average SIB number. It is the fineness modulus gives us weighted average SIB number, right. What we do is we give the SIB number, list size as 0 or then 1, SIB number 2, 3, 4, etc., etc. And these numbers are these numbers. So, if I want to find out an average weighted average SIB number, then the weighting functions are nothing but P 1, P 2, P 3, where P 1, P 2, P 3 are nothing but the proportions of that size aggregate in the total aggregate, proportion of that size aggregate in the total aggregate. Right. So, this concept we will discuss in the next class in the beginning, and we will discuss one more concept called surface modulus, and surface modulus is in terms of specific surface. So, specific surface can be related to what is called surface modulus, and this concept is, for a sphere we know the specific surface is 6 by dp. Here we are defining the specific surface as the surface area divided by volume of surface area per unit volume. So, specific surface for each particle can be defined, and then we can define the surface modulus again in terms of a kind of weighted function, and we will look into this in the next class. So, therefore, we can summarize today's discussion in terms of what we have discussed is essentially packing. Fineness modulus and surface modulus we have just started, and next class we will look into this, and that is what it is. Now, while looking at packing, we have seen the principles of the packing density, how it changes in a binary mixtures, and extended this idea. One can extend this idea to ternary mixtures. We have also discussed concepts like loosening effect and wall effect, which leads to particle interference. Thank you very much.